Hello, I'm going to go over some basics of eigenvalues and eigenvectors and also try to give you some sense of why we might be interested in them, if you're not already aware of why we'd be interested in the first place. So let's start with an example. We're going to take A to be this 3 by 3 matrix and X to be this 3 by 1 matrix. Typically we think of 3 by 1 matrices as vectors or 2 by 1 matrices as vectors. We will talk more about vectors at the beginning of chapter 4, but for now it's a 3 by 1 matrix. And when I multiply A times X, I actually get negative 6, 0, 2. And what you will notice is that negative 6, 0, 2 is actually 2 times our original matrix, 3 by 1 matrix X. So when I take A and I multiply A times X, I just get out 2X. So multiplying by A is the same thing as multiplying by this scalar 2. So we call negative 3, 0, 1 an eigenvector, and 2 its associated eigenvalue. So this is an eigenvector of A and an eigenvalue of A. So let's get down to a more concrete definition. An eigenvector of an n by n matrix A is a non-zero n by 1 matrix X such that AX equals lambda X for some scalar, that should say some scalar lambda, not X. So that's a lambda, that should be a real number. So essentially multiplying by A is the same thing as just multiplying by a real number. It is scaling X. And we call lambda the eigenvalue associated with the eigenvector X. So lambda actually goes with particular eigenvectors. So let's do another example. Example 2, here we have two matrices, 4, 3, 1, 2, and 3, 1. So let's compute 4, 3, 1, 2 times 3, 1, and we get 15, 5. And if you notice, 15, 5 is actually 5 times 3, 1. So we would say 3, 1 is an eigenvector, and it has eigenvalue 5. Matrices can have more than one eigenvalue, and they can have infinitely many eigenvectors. So it is also true that negative 1, 1 is an eigenvector of 4, 3, 1, 2 with eigenvalue 1. So that's something that you should try to verify for yourself. Notice I have different eigenvectors that have different eigenvalues, and not every vector is an eigenvector. So one thing that I forgot to just emphasize is that in this definition, notice that in order to be an eigenvector, the matrix must be non-zero. So it can have zeros in it, as in this example here, but it can't be all zeros. Okay. So let me actually pause here and let you see what's happening geometrically. Okay, so here we have a grid. It's an XY plane, and you'll notice that over on the left, we actually have the matrix M that we were just talking about, 4, 3, 1, 2, and remember that 3, 1 was an eigenvector. Okay, that's what's over on the left-hand side. So if we actually think of 3, 1 as a vector, it is this vector that's drawn right here with x value 3 and y value 1, and it is pointing in that direction. So we think of vectors as having a length and a direction, and here's this one. Okay, so what we want to do is actually visualize what's happening when we multiply our matrix times its eigenvector. So when we take our matrix times our eigenvector, this is what we get. So we're actually going to open up another piece here. It's the computer algebra system, and we're actually going to multiply that matrix times the eigenvector, and we get 15, 15, just like we did before. But let's look at what happens if we graph it. Look at what happened. The graph of this vector is just a vector in the exact same direction, only 5 times as long. So I have multiplied my eigenvector times the matrix and ended up with a vector in the exact same direction but 5 times as long. So this should visualize what's happening here. Okay, so what's an eigenvector? It's an eigenvector of a matrix is one where multiplying by the matrix is the same as multiplying by a scalar. We can visualize this if we try to visualize a vector and multiplying that matrix is the same. The result is a vector in the same direction, but maybe scaled, in this case scaled by a factor of 5.